So now that we've talked about light, some of the properties of electromagnetic radiation, some of the relationships between the wavelength of light, the frequency, its relative energies, and so forth. And we looked at Planck's equation to calculate the energy of light. We want to relate this back to what we started talking about, and this is Bohr's emission spectra experiment. Okay, and we recall that we stated that Bohr did most of his experiments with hydrogen gas, and hydrogen gas is diatomic. That means hydrogen is bonded to itself, and it's colorless at room temperature. Now, what Bohr did, and we're just kind of reiterating his experiment, what Bohr did was he took a cathode tube. Okay, so he took a cathode tube, right, and in that cathode tube he basically added a voltage source and he ran an electrical current through the cathode tube. So in the cathode tube we had hydrogen gas. It was completely colorless. What Bohr did was he ran an electrical current through the cathode tube from this voltage source. So this is your voltage source. If you've never taken physics, this portion is a positive terminal, this is a negative terminal. And what Bohr did was he ran an electrical current through the cathode tube, and this colorless gas that was initially seemingly colorless now actually started to glow red. Okay, so this is what we saw happen, and Bohr wanted to explain, okay, why did it emit a certain light, right? This is why it's called an emission spectra, right? Different species, different elements, different pure substances, compounds, they will express different spectras. They will release different emission spectras of light. Okay, so we want to explain why this actually happened, and Bohr actually explained this. And how he explained this, we know that hydrogen is basically contains one proton and one electron. It has 0 neutrons. This is one of the reasons why hydrogen is so reactive, right? We're looking at elemental hydrogen, right? So because Bohr used hydrogen, the model for this explanation was a lot more simpler, right? And what Bohr stated was that basically species, elements, contain different energy levels. Okay, so elements contain different energy levels, right? And he stated that the lowest energy level of an element or an atom is called the ground state. Okay, so the ground state is the lowest energy level of some kind of atom or element or ion, whatever the case is, right? So he looked at, so the ground state is the lowest energy level. So in his diagram, right, so let's say that this is an example of an energy level, right? And this is your electron. Okay. And let's say that each of these lines represents an energy level, and the higher up the lines are, it's a higher energy level. Okay. So these are different energy levels, and we're going to use n to represent an energy level. So this is n is equal to 1, the first energy level, n is equal to the second energy level, n is equal to 3, and so forth. Okay? And the lowest energy level, this is something called the ground state. Okay, so the ground state is the lowest energy level, and that's basically where the electron is going to be located if energy isn't being added. Now, what Bohr stated was that when you pass the electricity through this cathode tube that contained the hydrogen, right, when this electron gained energy, so let's say that this is the energy that this electron gains, right, when the electron gains energy, right, what happens here is it jumps to a higher energy level, right? So when electrons gain energy, they jump to a high energy level. So I'm going to redraw the energy levels, and you guys can kind of see what happens. But now the electron will basically jump from the ground state to another higher energy level, which looks like this, right? So it's basically jumped, okay? And this jump to a higher energy level, well, first of all, the higher energy level is called an excited state. Okay, so we'll call this n is equal to 2, n is equal to 1, and once again, these are just energy levels. And now the electron jumps to the higher energy level, right? And it enters its excited state. Okay. Depending on how much energy it absorbs will determine its jump, right? So jumps to different energy levels are dependent on the energy absorbed. Okay, so depending on how much energy the electron absorbs will depend on its jump. And now this electron jumps to a higher energy level, it jumps to the second energy level, its excited state. And these jumps are what we call transient jumps. A transient jump is a temporary jump. Okay, so transient means temporary, so it's a temporary jump. And what a temporary jump is, it's a jump that doesn't last too long. Basically, the electron will fall back down to ground state, right? So you know how it enters the excited state, it'll actually kind of fall back down again. Right, very temporarily. It'll only be there for a couple of seconds, like a fraction of a second, really. Right? Now, when the electron falls from the excited state to the ground state, whatever energy it absorbed, it's going to release. Right? Now, when it releases this energy, so when it falls back down to ground state, right? So when it falls back down to ground state, let's say that this was the n is equal to 2, and this is n is equal to 1. And when this electron kind of falls back down to ground state, it releases the energy absorbed, but it releases that energy in a different form. It releases it as a light energy. It releases it as a series of photons. Okay, so it releases it as photons. Okay, so this energy gets released after being absorbed. So this was the energy absorbed from ground state. Electron enters the excited state. This is a transient jump, so because it's a transient jump, it's a temporary jump, the electron will fall back down, and when the electron falls back down, it releases this energy. Okay? When it releases this energy, the energy released is a specific frequency and wavelength of photons. So this will be characterized by a particular frequency and wavelength of the photons. And that will create different colors, right? So when Bohr saw red, he basically saw the energy that was being released had a red wavelength, right? So the wavelength that was being released was on the red scale, right? So that wavelength would be closer to 760 nanometers. Right, so it's a pretty low energy wavelength. Now, what Bohr saw later on is that when Bohr increased the electricity, right? So specifically, he increased the current by increasing the voltage. So when Bohr increased the voltage, what he saw was, and I'm just going to redraw the diagram here just to demonstrate that. Okay, it's my masterpiece. Okay, so what Bohr saw, so when you increase the current, and say that this is a stronger current this time, okay, and it's going through, and there's still this, it's a different apparatus, so there's more hydrogen gas now. So he did the experiment again, and the colorless gas now, this time it actually started to glow orangish. Instead of red, it was glowing orange. So we're gonna ask ourselves, okay, what's happening here, right? Why is, it's like, it was red, now it's like reddish orange. Okay, why is the color kind of changing? Okay, why is the color changing? So Bohr's explanation for this is that once again, he stated that there is these energy levels in an atom, right? And we looked at these energy levels using N. And now what's happening is that these electrons are actually absorbing more energy. So once again, we start again with the ground state. So this is the ground state. The ground state, once again, is the lowest energy state of an atom, and thereby its electrons. And now when this guy gains energy, so let's say that this is the energy that it gains, and this is a larger amount of energy. Okay, it gains a larger amount of energy. Now what's happening is the electron jumps to a higher energy state. Okay, so the electron actually jumps from ground state all the way. Okay, so it jumps from ground state all the way to, from the first energy level all the way to the third energy level this time. This is a bigger jump. Okay, it's a larger jump. But once again, so now we're at a new excited state. So we're at a new excited state. Right, state. But once again, these jumps are transient jumps. So because it's a transient jump, the temporary jump, because it's a temporary jump, the electron will then eventually fall back down to ground state. So when the electron falls back down to ground state, it releases the energy in a certain number of photons with a particular wavelength and frequency, right? So in this case, the electron falls back down from the third energy level back to the second. So this is n is equal to 3, n is equal to 2, n is equal to 1. The energy that it absorbed gets released as a certain wavelength of photons. So this time, the energy that gets released is an orange characteristic of orange wavelength, right? We see orange because our eyes perceive that form of energy as the color orange, right? So this is the energy of the photon that gets released with the wavelength and frequency characteristic of orange visible light. Okay, so the conclusion, so this is what Bohr actually observed from his experiment, and he came up with a series of conclusions regarding his experiment, right? So one of the conclusions that Bohr came up with regarding his hydrogen emission spectra experiment, so one of the conclusions that Bohr kind of came up with was that what Bohr actually observed was as he increased the current of the electricity, there was different wavelengths that were being created, and those wavelengths were actually shifted from red, orange to a yellow, right? And we understand that according to our study of wavelengths and energy of visible light, we know that red has the highest wavelength, and violet here has the lowest wavelength. And this is also kind of associated with the lowest energy. It's inversely proportional. Red has the lowest energy of the photons, but violet has the highest energy. Okay, so violet has the highest energy, red has the lowest energy. And what Bohr saw was there was a shift from red to orange to yellow. So this implies that the wavelength of light that was being released had a shorter wavelength, higher energy. So ideally, there wasn't a set number of energy levels. You could have an infinite number of energy levels because you can have an infinite shade of each spectral color, right? Each spectral color can have a different gradient in terms of its hue. So there's basically an infinite number of hues that are possible. So the idea here is that Bohr stated one of his conclusions, and we're going to look at some of the conclusions of his experiment. Right, one of his conclusions was that an atom contains an infinite number of energy levels. Right? Each energy level is called shells, right? So each energy level is called a shell. Specifically, we can call it an electron shell, right? I'm going to use N for energy levels, so electron shells. Okay? And Bohr then stated that electrons orbit around the nucleus, and that they are attracted by the positive charge of protons and that these orbits are called electron shells. Okay. And Bohr also stated that electrons in the same shell have the same energy and vice versa due to the relationship between the force of electrostatic attraction and distance, right? Specifically the separation distance. Okay, so these are some of the rules that Bohr created, right? And he put all of this together and he stated that electrons orbit the nucleus, right? Electrons orbit the nucleus containing protons and neutrons. Now, before we actually reiterate his planetary model, I want to look at the third tenet really quickly. Electrons in the same shell have the same energy, and vice versa, due to the relationship between the force of electrostatic attraction and separation distance. Let's take a look at the third tenet. Okay, so we know that according to Bohr's planetary model, okay, we'll call this, say this is a proton. This is a neutron. Okay, actually, you know what? Let's use that for electrons. So this is a neutron. And this is an electron. Okay. Let's take a look at a elemental helium, a helium atom. So elemental helium atom has 2 protons, 2 neutrons, 2 electrons. So 2 protons, positive 2, 2 neutrons, 0, 2 electrons, negative 2, sets up to 0. Okay, so a helium atom is actually going to look like this. So it's going to have 2 protons in the nucleus, and then the neutrons that are kind of just in between the protons, right? And the neutrons are attached to protons via the strong nuclear force. And the strong nuclear force is the strongest force that's present in nature. This is the same force that is being used for atomic weapons, right? The force between atoms and protons and neutrons are so strong that when they actually get separated through a fission reaction, they basically release a tremendous amount of energy, and that energy causes other protons to split from neutrons. The strong nuclear force is the force that keeps a proton with a neutron. Now, the electrons are being held together by a weaker force of attraction, but still pretty strong because the size of a proton is almost 2,000 times bigger than a neutron, right? And this is the orbit of, let's say, the 2 electrons that orbit around a nucleus. And you want to think about this in a 3-dimensional model, right? So we can count the nucleus as all of this space here. I'm going to draw a 3-dimensional. So this sphere here represents the space that governs the nucleus, and this is basically the space that will govern where the electron is located relative to the nucleus. Okay, so this is where the electrons are located relative to the nucleus. Now, what we need to understand here is how does the distance affect the energy of an electron? Well, we can understand that the nucleus contains protons, and protons have a positive 1 charge, and the mass of a proton is approximately 2,000 times greater than the mass of an electron. So one proton has a very significant charge, or significant force of attraction on an electron, right? So the force of attraction a proton has on an electron, I'm going to call it Fe. Okay, so this is the force of attraction, specifically electrostatic attraction. So Fe is the force of electrostatic attraction, and the force of electrostatic attraction is the force between positive and negative charges and negative and positive charges, right? Now Fe can also be used for the force of electrostatic repulsion. If the charges are opposite, we're going to have attraction. If the charges are the same, we're going to have repulsion. There is an equation for the force of electrostatic attraction, right? And that's associated with Coulomb's constant, the charge of the first particle times the charge of the second particle over r, the separation distance. So we're going to take a look at, we're not going to look at this equation per se, but we need to understand a few things, right? So if Q1 times Q2, and Q1 and Q2 are the charges, are less than 0, then we have electrostatic attraction. Okay, so electrostatic attraction is associated with a negative Fe value, because Fe is going to be less than 0. If Q1 and Q2 are greater than 0, we have electrostatic repulsion. Now, we're not going to look at electrostatic attraction so much. We're going to look at electrostatic repulsion. Now, K naught is a constant. It's called Coulomb's constant, but we're not going to look at this. This is more of a physics kind of discussion, right? But the Coulomb's constant does have a certain value to it. And R is something called separation distance, which we're going to look at the relationship of in a second. Okay? You can notice here that the force of attraction and the separation distance are inversely proportional. We're going to explain why this is the case. But for the time being, the force of attraction, electrostatic attraction, is the force that attracts electrons to protons. Okay, and because it's a force, we're going to use this the symbol newtons, the unit newtons, to represent that. Now we can understand that the force of electrical attraction is inversely proportional to the separation distance. R, the separation distance, is the distance of the charges. Okay, so separation distance is going to be in meters. It's going to be the distance of the charges. Okay, we use for charges, we're going to use Q, right? And Q is a charge, and charges are measured in the unit coulombs. Okay, so coulomb is the unit for charge. I'm going to use C for that. Okay, I'm going to explain why when the separation distance increases that the force of attraction decreases, and why when the separation distance decreases that the force of attraction increases. Well, we can understand that we know that the force of attraction is going to decrease with a larger distance, because now the electrons are further away from the protons. It's like when you take two magnets together and you take a north and a south pole. The further you bring the magnets, the weaker the force of attraction. So the force of attraction is a function, it's dependent on the separation distance, right? Now, why is this important? Why are we even looking at this, right? Well, we understand that the separation distance of force of attraction will be useful in determining the energy of an electron. Okay, specifically we're going to be looking at the kinetic energy. So normally if I take an electron and I throw it into free space, so this is just an electron floating around in space. Okay, so this is our electron, and without any kind of attachments, this has a constant kinetic energy. Okay, but now that you add a force to it, if there's a force that's being applied to that electron, let's say that there is a force of attraction that this electron feels, right? So let's call this guy the force of attraction. now the kinetic energy is going to be affected, right? And what happens here is that the kinetic energy is being dependent, right? The kinetic energy is dependent on the force of attraction. So if the force of attraction increases, the overall kinetic energy of the electron decreases, right? Kinetic energy is the ability to move. The force of attraction inhibits or prevents movement. So as there is a higher force of attraction on an electron, the electron's energy gets reduced, right? Now when kinetic energy decreases, an electron will become more stable. So stable means low energy. So ground state is a stable state. Reactive means high energy. Okay? So as the force of attraction increases, the kinetic energy decreases, and as the force of attraction decreases, the kinetic energy increases. Okay, so it's a really important property to understand, but this is also related to the separation distance, because we stated that separation distance affects the force of attraction, just like having two magnets. The further you move the charges or the magnets, the weaker the force of attraction is, and vice versa. And this is also true for repulsion. So as the separation distance increases, the force of attraction wanes or decreases, and as the force of attraction decreases, the kinetic energy actually increases. Okay, so the further electrons are from a proton, the weaker the force of attraction is from the proton to the electron, and as a result, the kinetic energy of the electron is higher. And this goes back to being stable or reactive. High energy means high kinetic energy. Low energy means low kinetic energy. So an electron would be more reactive. So as reactivity increases. Okay, and vice versa, as the separation distance decreases, the force of attraction will basically decrease, Force of attraction decreases, right? Oh, sorry. The force of attraction increases, made a mistake there. Force of attraction increases. So as the separation distance decreases, the force of attraction increases. And as a result, the kinetic energy decreases, and now the reactivity of the electron decreases. So it's a really useful relationship to understand, right? And the reason we're looking at the energy of electrons is because the energy of electrons are important in chemical reactions, and chemical reactions are governed by chemical reactions they occur by changes in electrons, right? And specifically, so because there's changes in electrons, electron energy is very useful. Okay? So this is really useful in helping us to understand how elements will react to form compounds, which we'll discuss later. But specifically, why we really focus on the valence shell, the outer shell of electrons, which contain the electrons that are the furthest away from the nucleus, because those are the highest energy electrons, right? So we'll take a look at that when we draw this. So if we're looking at Bohr's atomic structure, the planetary model states that the nucleus is in the center of the atom and it's being orbited by electrons, right? So let's do an example of an element, right? So let's take a look at, and when I'm looking at elements, I'm going to use the chemical symbol X, Z, and a symbol A. Okay, now A represents the atomic mass. Z is the atomic number. And this is your chemical symbol. You can have different symbols for chemical symbols. The atomic number is the number of protons. Now this is really important in the nucleus. This is really important because each atom, or each species, each atom is governed, well, let's just say each atom's identity is governed by its number of protons. So what that means is each number of protons represents an atom's identity. So if I say 6 protons, that identity of that atom is always carbon. If I say 10 protons, the identity of that atom is always neon. So it doesn't matter what the charge of the atom is and so forth. If you have 10 protons, it's always neon, right? Or if you have 20 protons, it's always calcium. Okay, so the atomic number is the number of protons, and it's the identity of the atom. The atomic mass is the number of neutrons plus the number of protons, right? So N is going to be number, just going to rewrite that, the number of neutrons. And atomic number we said is number of protons. And we know that the neutrons and protons make up more than 99% of the mass of an atom. So because it makes up 99% of the mass of an atom, all of the mass can be generalized as the mass in the nucleus, right? So the mass of the nucleus is the atomic mass. And this can be generalized as the mass of the atom. Okay, now although electrons do have a mass, it's very small, so it's negligible, we don't consider it, right? So when we're looking at an atomic structure, let's say we're looking at the structure nitrogen, which has an atomic number of 7, and atomic mass, let's say it's 14. So this means, because it's elemental nitrogen that we're going to be looking at, this guy has 7 protons, 7 electrons, 7 neutrons, right? These two should add up to 14, right? And all the charges should add up to 0. And the number of protons should equal to the number of electrons because this is an element. If we wanted to draw the structure out, what I'm going to do here is I'm going to draw out the nucleus, right? So I'm going to draw out the nucleus here. And in this case, the nucleus has 7 protons, 7 neutrons. And the electrons orbit around the nucleus in shells, right? So this is according to Bohr-Rutherford structure. So this is the first energy shell, or the first orbit. And this is the second energy shell. Okay. Usually what they'll say when you're drawing this is electrons are usually grouped in sets of 2. And each set of 2 is called an orbital. And we'll talk about this more. We'll talk about this more when we look at the quantum mechanical model. So you could group the electrons like that as well, but for the time being, I'm just going to represent them separately, right? So the first shell can actually hold a maximum of 2 electrons, right? And this is because it only contains 1 orbital. And the second shell can hold a max of 8 electrons. So let's just know that for the time being. Okay, and we can see that there's 2 shells in this atomic structure, right? And we also talked about the energy of electrons relative to their separation distance. So if this is electron 1 and this is electron 2, electron 3, electron 4, 5, 6, and 7, we're looking at relative distances. Say we're looking at, this is the distance, R to the second shell, R2, right? We'll call it R5 for the distance from the outer shell to the core. And we looked at the distance here, right? The energy of electron 5 should be equal to the energy of electron 6 because of the fact that the separation distance of 5 should be equal to the separation distance of 6, right? However, if we're looking at the distance from 1, if we're looking at the energy of electron 1, right? This one should be much lower than the energy of electron 5 because the separation distance of 5 is greater than the separation distance of 1. Okay, so this is how you can relate the distance of an electron and its relative energies, right? That the energy of an electron is dependent on its distance from the nucleus, or in other words, the energy of an electron is dependent on its position in the atom.